Our previous lectures went over work and kinetic energy and the relationship between work and kinetic energy. Now we're going to be talking about potential energy. Remember that work is the result of applying a force over some distance, and that force and that distance must be parallel to one another. And that energy is the ability to do work. And we've talked a little bit about potential energy being the potential to be able to do work. So, energy due to motion is kinetic energy. A moving object has the ability to do work by virtue of its motion. Energy that depends on a force and a position relative to surroundings is potential energy. All right? In this situation, that force has the potential to do work due to its position relative to other objects in a surroundings. There's a bunch of different types of potential energies that match their related forces. We're going to be talking predominantly about gravitational potential energy, or the force of gravity and its potential to do work due to its position. And we'll also be talking about elastic potential energy, or the potential for a spring or spring-like object to be able to do work depending on the force of the spring constant, or the force of the spring. So I did say that elastic potential energy was one example. So here we can take a look. An example of potential energy would be the wind-up toy. You see, a wind-up toy has a spring in it, and when you wind that toy up, you compress the spring, or when you wind that toy up, you stretch the spring out. Either way, someone is doing work to wind up that toy. Somebody is applying a force, and that force is getting applied over the distance. One way that we could look at that force over a distance is we could look and we could say, well, normally our spring is like this, but if I apply a force on the spring, well, now look, that force got applied over that distance. So I've done work on the spring. And as long as that spring is held in that position, the spring now has the potential to do work. And if the spring does that work, it'll do it over that distance. Alright, so this has everything to do with the position of a spring relative to its surroundings. You see, our spring, when it's completely relaxed, there's no potential energy. The spring has the ability to hold a force in it, that you have to apply a force to the spring to compress or stretch it, but just the fact that this spring has the ability or has a force related to it, the spring force, doesn't mean that it has any potential energy, which it doesn't right now. However, if I do work and I store that force, that spring then has potential energy, and it's due to the spring force right here and the position of the spring relative to its surroundings. This spring would not have any potential energy in it if it weren't compressed like this relative to its surroundings, or stretched relative to its surroundings. However, because of the force and because of the surroundings, it has potential energy. The most common form of potential energy is gravitational potential energy. Take this brick, for example, which has potential energy due to the force of gravity and its position relative to the Earth's surface. If the Earth's surface were right here, much like sitting a phone down on a surface of a table, relative to the surface of the table, it doesn't appear that there is any potential energy. However, if you raise an object up relative to a surface, now it has the potential to do some work because it can move. So this brick, if we assume that it is some position above the ground, now this brick at this height has potential energy, and this potential energy is due to the force of gravity and the position relative to the surface of the earth. Now this brick could do work. Has the potential to do some work. The ability to do work in this situation is because of its position. This brick has a force of gravity applied to it at all times. You experience the force of gravity at all times. That's your weight. However, you only have potential energy as a result of that force when your position allows it, or your position makes it so. And once that position is in place, now you have the ability to do work. Once I climb up to the top of Mount Everest and hold you by the scruff of your neck over the edge, now you have the potential to do some work. All I have to do is allow gravity to act over some displacement. And then you'll fall to the ground and do work. Remember that when I say do work, I mean apply a force over a distance. The force in the case of gravitational potential energy is the weight of an object. The distance is how long your force is applied. So if we're talking about you experience gravity, and I drop you off of some surface, right? The force that you experience as you free fall downward would be mg, and the displacement that you would experience that force is here, some distance. So that means that the work that gravity does on you here is going to be equal to the force times the displacement. We'll do cosine theta. Which here the cosine of theta would be 0. And so that means that if I did this, gravity would do some work on you. Likewise, if here you are, and you're a falling object, and here we'll say there's some stake or something in the ground. Right, here you are falling down, and whatever speed you have now as a result of falling, you'll fall and you'll hit this stake in the ground, and you'll apply that force, the force that you have of falling, and it will move the stake or drive the stake into the ground some distance. So here in this situation, the work done on the stake would be the work of you being you experiencing your potential energy getting transformed into kinetic energy. And now you're going to apply that force, mg, over the displacement of the stake down into the ground. And again, cosine theta would be 0. So here, we know that if something is allowed to fall to the ground from some position above the ground, then the object will be able to apply its force, its weight, over a distance, just like driving a stake into a ground or dropping you off of Mount Everest. And that means that by virtue of the force of gravity and by virtue of the height above the reference point that you were lifted, that you could do work. So that's potential energy. But there's a few things we have to take a look at, and these are going to allow us to quantify potential energy in some really meaningful ways and give it a nice relationship to work. If you want to lift something, you have to do work, which means you have to apply a force over the distance up that you want to lift it. So let's go back to our brick example. Here, if you want to lift the brick up, you must apply a force, and the force of lifting something is, we'll say this is the force exerted by the hand, and in order to do this with uniform motion, we always want to assume uniform motion. The force that you're going to exert is going to be equal to the weight of the object, because if the forces were unbalanced, you would accelerate. Your force is going to be applied upward, and that's going to cause this brick to be displaced in an upward direction. So that means that the work exerted by you as a result of the force exerted by you times the displacement of the object times the angle of separation between them. Now here the angle of separation between them is 1. Here your force is equal to mg, so the work that you must do on the brick to get it up here is going to be equal to mg, and then the d we'll assume that you started from down here. We'll assume that you started from this position down here and that you ended at this position up here. So that means that your displacement is going to be y2 minus y1. So that means that the amount of work that you do depends on the weight of the object and how much it's displaced from an initial position. If we're assuming from y2 to y1, then it would actually be that amount. All right, and that's going to be the work that you must exert on an object in order to lift it up. However, if gravity were going to cause an object to fall down, then that means that the object is going to be falling down and that gravity is going to be acting down. So that means the work done by gravity would be mg y1 minus y2, and that would be assuming this downward motion. All right, and in this case, remember when we were going up, all right, your force was up and your displacement was up. Now when you're going down, all right, gravity is down and your displacement is down, and so that means that the cosine theta is going to be 1 in both cases because theta is 0 in both cases. So what we can do is we can define some of these variables now. We can define, remember we said that the work done to lift an object up is going to be equal to the object's weight times the change in its position. So that means that we can say that gravitational potential energy is this variable now. We can define it as saying due to Earth's gravity, it's the product of the weight and its height above the ground or some reference level. So now when you see an object and it has a weight and it's some position above the ground or some other reference level, then you could say, well, this quantity here, mgy, is the potential energy that that object has at that location. So one of the things that I want to point out is that we say the ground or some reference level. All right, and here's why we say the ground or some reference level. So here we'll call this the ground, and here we'll call this a table. Now, Benny is holding one cell phone above a table, and with his really long arm he's holding the other cell phone above the ground. Now he wants to know the potential energy of each of these cell phones, and there's two ways to quantify it. One is we could quantify the amount of potential energy for each cell phone compared to the ground. Or we could say we would like to compare the potential energy of the cell phone above the table and this cell phone above the ground. In this case, we wouldn't be doing a direct comparison, it'd be a comparison to a reference level. And why would we want to do that? Well, here gravity is going to work across this height, and here gravity is going to work across this height. So that means that the potential for this cell phone to do work is going to be based off of when it will hit the table, or how far above the table it is, and this one above the ground. So we could say for this cell phone, for cell phone 1, we could say that y1 equals 0, and we'll call y1 the table. And for this cell phone 2, we could call y1 the ground and y2 this position. And now this cell phone and this cell phone, even though they're at the same height, we would say that this cell phone has more potential energy than this cell phone, and that's because of our reference label. If I want to know the potential energy it has compared to where it's going to stop, then this is a really convenient thing to do. Then you're only looking at the differences in height compared to that reference level. And so that brings up another point, which is the higher the object is above a reference level, the more potential energy due to gravity it has relative to that reference level. Right? An object that's 2 meters above the ground would have more potential energy than an object that was 1 meter above the ground, and it would have less potential energy compared to an object that was 4 meters above the ground. So we take a look and we say that the work that it takes to move an object up is going to be equal to the weight of the object multiplied by the change in position that we have. So how high above a reference level. And since we said that mgy is a potential energy due to gravity, if we distributed this, we could say that the work exerted equals mgy2 minus mgy1. Alright, so now we've got the work equals the potential energy at the final position compared to the potential energy at the initial position. And final minus initial is change. So that means that for any object, the work that must be exerted is going to be equal to the change in potential energy. And that relationship is a really convenient relationship that will always hold true. The work done by an external, so this is the work done by an external force to move an object of mass m from point 1 to point 2. And that's saying that the work that's done by an external force to move it from position 1 to position 2 is going to be equal to the change in potential energy from position 1 to position 2. We could also take a look at work done by gravity. See, this work was done against gravity. It was done to move an object upward. In terms of work done by gravity, well, in this case, gravity is a downward force, and so we set downward to be down for weight, and now we look at the exact same situation, and we end up saying that the work done by gravity is opposite the potential energy. And here's another way to look at that, is the work done by gravity is going to be equal to the object's weight, only this time, if gravity is moving downward, it would be starting at y2 and ending at y1, so it would be y1 minus y2. And if you had those previously set, y2, y1, and it's moving down, that's also where that negative sign comes from. However, if you flip-flopped them and you called one of them y1 and the other y2, that's where the negative sign comes from, and that's by directing your axis. It's really important to remember that potential energy belongs to a system, not just one object. If Benny took an object and he put that object all the way out into space where there was nothing else around, this object has no potential energy because without a system, there's nothing to reference it to. However, if that same object this is a no system object, and this is a system object. Now, not only do we have force of gravity, but we also have a system, which includes the Earth, the object, and we have a force. Now, with this system, this object has potential energy, and it's because the system has potential energy. The object all by itself has nothing going for it. And also remember, just like we discussed before, that gravitational potential energy is always compared to something. So you always have to set your very own reference level, and you can set it however it's convenient. And the fact that you can set it however it's convenient for you is really going to be nice for doing calculations. So a few things to remember when you're problem solving for potential energy is that you only need to know how much the potential energy is changed, and that means that you can set a convenient reference point. The potential energy change will always be the work done to cause it to make that change. So you're only ever going to need to consider a height difference. You will never have an absolute height. And one of the things to consider is, just like in the example of Benny dropping the cell phone, if the cell phone is 2 meters above the ground, but going to hit a desk that's 1 meter above the ground, well, then you'd only want to know how much the position of the cell phone is going to change, which would be from the 2 meter height to the table. So it's convenient in that situation to set your reference level at the table. If, however, Benny's going to drop your cell phone on the ground, then you'd probably want to consider the ground your reference point, because you'd be interested in the change in position from the 2 meters all the way down to the ground. Another thing to consider that's incredibly important is that gravity can only do work in a vertical direction, on a vertical axis. So that means that you don't have to worry about how an object gets from its initial position to its final position. If you're considering the change in gravitational potential energy, you only need to know the height difference. It doesn't matter if an object is falling straight down, or if it's taking a squiggly path, or if it's traveling along a plank. All that matters is that the force must be parallel to the displacement. And if the force is gravity, mg, and mg is always down toward the center of the earth, then that means that the only displacement that object can have a force over would be some height. And this is our relationship. Remember that you have F times d cosine theta equals work, and work equals change in potential energy. So that means that if an object is traveling straight down, right, the force, and in this case the force of gravity, is parallel to the height, and so that will give you force times height, mgh, will give you the change in potential energy, which will give you the work. In this situation, it's following a really weird non-vectorial path, but overall, for this situation and this situation, right, for that angle, well, here your force mg is downward, and it's traveling along this distance here, and the force and the displacement are separated by this angle theta. So in both of these situations, it's going to be mg d cosine theta for both of these situations, and d cosine theta equals h. So there's two ways to prove. One of them conceptually. Work done by gravity can only be in a downward or upward direction. It can be either positive or negative, and as a result, only the vertical height is going to determine how much the potential energy changes or how much work is done. In the other situation, when you consider an object moving along an incline to go up or down, well, the work is only done by a force and a displacement that are parallel. So that means that only the vertical force and the vertical displacement will do any gravitational work. So here we've got a roller coaster, and it's going to allow us to consider example 6.7, which is changes in potential energy for a roller coaster. We're going to be taking a look at two different ways to calculate this change in potential energy. The first is we're going to calculate the gravitational potential energy at point 2 and point 3 relative to point 1. So at first we're going to set point 1, we're going to say is 0. So point 2 is 10 meters above point 1, point 3 is 15 meters below point 1. So we're going to figure out the work done at point 1 is going to equal the potential energy at point 1. So that's going to be mgh, or sorry, I'm going to use mgh a lot. That's what it is traditionally in college prep physics. But anytime I say h, remember h equals y2 minus y1. So we set the first position to be a 0 position, and we want to know the work done to get it to point 2. So the work done to get it to point 2 is going to be equal to the change in potential energy. And we're considering PE2 minus PE1. So here PE2 is mgy2, and here PE1 is mgy1. We set y1 equal to 0, so that's going to be a 0. mgy2 is going to be the mass of this roller coaster. It was set to 1,000 kilograms. So it's going to be 1,000 kilograms times 9.8 meters per second squared times 10 meters, or the difference in potential energy from point 1 to 2, or the work done to go from point 1 to 2, is going to be equal to 9.8 times 10 to the 4th joules. And we can also consider the change in potential energy from point 1 to point 3. And here work is going to be equal to the change in potential energy, and that's going to be PE3 minus PE1. And here PE3 is mgy3 minus mgy1. That's still equal to 0. And now we have 1,000 times 9.8 times, now that's a 15 meter. And that 15 meters is in a downward direction. And so our change in potential energy, or our work done to get to that point, is going to be negative 1.5 times 10 to the 5th joules. And now we can calculate the change in potential energy from point 2 to point 3. Alright, so now we can do work equals change in potential energy, and that's going to be mgy3 minus mgy2. Now we've got a positive 10 and a negative 15, so I have mgy3 and mgy2 here. So I'm going to take mgy3 negative 1.5 times 10 to the 5th joules, and I'm going to subtract 9.8 times 10 to the 4th joules, and I get the change in potential energy from point 2 to point 3 is going to be equal to negative 2.5 times 10 to the 5th. Alright, and that tells us how much energy change was from here, delta PE, or how much work was done here. So now we had, this was our first, we were calculating how much work was done to get the roller coaster up. And then we were calculating, compared to the first part, how much work was it to get the roller coaster down. And then we wanted to know, well, from the very top, how much work was it to get the roller coaster all the way from the top to the bottom. And we were able to calculate. And in both cases, or in all three cases, it makes sense. You did negative work to get a roller coaster down because gravity was doing the work. You did positive work to get the roller coaster up because you had to exert that force against gravity. And overall, the change in work was negative because the change in displacement was negative, which means that gravity did all the work. We can repeat that, but this time we can change our reference point. And why would we want to do that? Well, if you know that your overall height change is going to be down to this lower level, and then maybe we want to set this value as 0. And in that case, this one would be a positive 15 meters up, and this would be a positive 25 meters up. And now we can calculate our potential energy from 1 to 2, from 1 to 3, and from 2 to 3. So here, from 1 to 2, work is going to be PE2 minus PE1, and so that's going to be mgy2 minus mgy1. This time y2 is 25 meters and y1 is 15 meters, and when you calculate that, you're going to get 9.8 times 10 to the 4th joules. And that makes sense because the difference between 25 and 15 is 10, the same value we used before. We could calculate the work done on an object, on the object from 1 to 3, so it would be PE3 minus PE1. And in this case, it's going to be mgy3 minus mgy1. Well, in this case, y3 is 0. mgy1 is a positive 15, and so you're going to end up with the exact same variable, negative 1.5 times 10 to the 5th joules. And then finally, we can calculate our work done from PE2 to PE3. Now here it's going to be mgy3 minus mgy2. The difference between y3 and y2 is still the same, and so we're still going to get that same value, 2.5 times 10 to the 5th joules. So again, it doesn't matter where you set your reference point, as long as you're using a consistent reference point, the change in potential energy is going to be the same. And so that's a great example of how you can use a potential energy position that is most convenient for your calculations. We're going to be taking a look at one other type of potential energy, even though there's more than one other type of potential energy, and that type is going to be elastic potential energy. But one of the things to consider is that no matter what type of potential energy you're looking at, each potential energy is going to be associated with a force, and that potential energy will always be opposite the work done by that force and positive for the work exerted against that force. And that's true for gravitational potential energy, and that's going to be true for all types of potential energy. So a change in potential energy is always going to be equal to the work required for an external force to move the object without acceleration. So we're always considering the potential energy to move an object with uniform motion between 2 points. So let's go ahead and let's take a look at potential energy related to elastic materials. Any spring has potential energy when compressed or stretched, because when it's released it can do work. Here I have a spring, a non-compressible spring. If I stretch this spring out, you know that this spring could do work. It could apply a force to my fingers over a distance. That's how much I stretched it out. And that would be the work done by the spring. Ow! Same could go for, where's my stretchy compressy spring? Here it is. Same could be said for compressing a spring. Alright, if you compress the spring, right, it can now do work. It can apply a force over that distance and do work. To hold a spring stretched or compressed, a length, x, from its natural or unstretched length, requires an external force that's directly proportional to how much you're going to compress it. So, in other words, this spring, set just like this, it's at its relaxed length. It's the length that it would be when there's no energy stored within the spring. If I'm going to compress that spring, the amount that I compress it is called x. So here we set its relaxed length. and now I compress it x. Alright, so I compressed it this amount. And the force that I had to apply was proportional to how much I pressed it. If I press it more, I actually need to apply more force because I have a greater x value. Alright, and the same goes for stretching. It's its relaxed length. If I'm stretching it, I have to apply a force, and that force is going to be proportional to how much I stretch it compared to its relaxed length. The length that the spring would normally be is called its relaxed length. Alright, so that means that any spring, right, has a relaxed length. Alright, if you compress it, you're going to compress it that amount. And it will store that energy within it. And the way that you know is as soon as you remove that force, the spring will shoot back to its relaxed length, applying this force that came from the compression of the spring over that distance. It only applies it over the distance x that it was compressed, and it causes it to do work on an object. That means that a spring force is not constant. It's only proportional to x. And we can calculate a spring force given the equation F equals kx. This is the force required by an external object. So this F equals kx is the force required for the hand to compress the spring this way. That would be F equals kx. In this equation, k is a constant called the spring stiffness constant, and it measures the stiffness of that spring. So if you had a k of 5 newtons per meter, that means that every meter that you compress that spring will require 5 newtons. Now that's a very lightweight, flimsy spring. If you had the kind of spring that would allow for shock absorption on a car, you might have a spring constant to the magnitude of, say, 586 newtons per meter, or potentially even thousands, 6.4 times 10 to the third newton meters. That would be an incredibly stiff spring, which means that every meter that you stretch it down, you are required to apply thousands of newtons of force. So that's what a spring constant is. The spring exerts a force in the opposite direction of the applied force. So this is the applied force. Now, when that happens, the spring, because forces come in pairs, is applying a force in the opposite direction. And so we say that the force that the spring applies, the force by the spring, is going to be opposite of kx, or negative kx. And this equation right here is called the restoring force, or spring equation, and it's given a name of Hooke's law. Hooke's law was developed by Hooke. Isaac Newton absolutely despised Hooke and spent a lot of his time trying to discredit the man. A lot of people think it's because Hooke was a little bit of a homely looking fella. So here we go. We could take a look. In this image, we say that this is the relaxed length of the spring. There's no energy being stored, so the spring does not have a potential to do any work. However, if we stretch the spring out by this amount, x, right, there is a pulling force, and that pulling force is going to be equal to kx, and it's in this direction. The spring then has an equal but opposite force of negative kx, which means that the spring's force is in the backward direction. If, however, we were compressing the spring this same distance x, now the pushing force is going to be equal to kx. It's the amount that the spring is getting pushed. And the spring is going to be negative kx. That's the direction that the spring is pushing back, equal and opposite. But in either case, the amount of force is dependent on x. And that's another way of saying, if you see that F equals kx, then that's like y equals mx. And so you know that there's a linear relationship between the two. And here it is. Here's the force dependent on the position of a spring. And if we take a look at that, we can see that as the spring is compressed or stretched more, it's going to require more force to continue to stretch or continue to compress. And so if we look at a situation and we want to know the work done, this is a non-constant force. So we could find the area under the curve. Here, because it's linear, the area under the curve is going to actually be base times height divided by 2, or the average force is going to be half of the force required at the final position, at the final stretch. So that means that since work equals force times displacement, and we're assuming that this is in the same direction, so we're saying cosine 0 equals 1. So here, the force equals kx, so the work is going to be the force, but we're looking at the average force, which for a linear force is going to be 1/2 kx. And it's going to be across a distance, and the distance that the spring is either getting stretched or compressed is the amount x, either stretched or compressed. So that's going to be 1/2 kx times x, or in other words, work done is going to be equal to 1/2 kx squared. And now we have this value 1/2 kx squared that we can define as elastic potential energy. And remember, the work done by the spring is negative the change in potential energy. The work done on the spring is going to be equal to the elastic potential energy. And the neat thing is that Hooke's law is going to be accurate for springs as long as x is not too great. You can ultimately stretch a string so much that you manipulate its surface. You could see this with bent springs and springs that no longer will hold their own elasticity. So as long as x is not too great for the material or the integrity of the material. The work for a spring will always equal Fx. X is the amount stretched or compressed. But since force is Kx and F varies with X, we then use the average force as given by area under the curve. So average force is 1/2 Kx, and work is going to be equal to 1/2 Kx squared. It's how much work must be done to compress or stretch a spring, that amount of x. Therefore, we say that work done by a spring will equal negative 1/2 kx squared. Work done on a spring would be positive 1/2 kx squared. So when a spring is compressed, it has the potential to do work of a value of 1/2 kx squared. And this is spring energy or elastic potential energy. So our value for elastic potential energy, which would be analogous to gravitational potential energy, is 1/2 kx squared.